Hello guys, today we are discussing isotopes and isobars. Now on today's new lesson on calculation in chemistry, we need to quickly visit some of the things we learned in our previous lessons. Now in our previous two lessons, we worked on relative molecular mass, that's molecular mass, and just in the most recent lesson, we worked on percentage composition. Now we need the knowledge of these two major things we worked on in our previous lessons to understand what we're about to discuss today. So today we're going to be discussing isotopes and isobars. So what are isotopes or what's an isotope? So an isotope is a phenomenon whereby the various atoms of an element have the same atomic number, that is the same proton number, but varying neutron number, which brings about varying atomic mass unit. So when we talk about an isotope, we are talking about a kind of condition, or I can call it a kind of phenomenon, whereby the atoms, don't forget that according to John Dalton, according to Dalton's atomic theory propounded in 1803, it was said that each element has identical atoms. That's what Dalton said. But down the line or along the line, it was discovered that various atoms of a given element could have different atomic masses, which is quite militating or quite different to what John Dalton propounded in his atomic theory in 1803. So quickly, we're going to be looking at isotope. Now we talk about isotope. An isotope, as we have said, is a condition whereby the same element, that is a particular element, not different element, the same element has different kinds of atomic masses, but the same atomic number. Now, why do we have that? The reason for this very phenomenon is simply this. Neutron number changes. As you can see, this is carbon atom. Now, this is a carbon atom, this is another carbon atom, this is another carbon atom. The same element you're talking about. Carbon is a given element, but in this very element called carbon, we have different atomic masses. Now, as you can see, this carbon 12 atom, it has here we have a carbon, here we have a 12 amine, 12 atomic mass unit. Why the atomic number, which is the amount of proton, according to the lessons we took in our previous, according to the things we discussed in our previous lesson, yeah, we have atomic number to be 6, why atomic mass is 12. So it means proton is 6, which is atomic number, why neutron is 6. That's it for carbon 12. Why for carbon 13, proton is 6, neutron is 7. So you can see there's a difference, a change in neutron. So neutron here is 6, neutron here is 7, and that's why we have carbon 13. It's the same carbon as an element, but this atomic, this atom of carbon, has 7 neutron, and that's why we have 13 atomic mass unit. So while this very one here, we have carbon 14. So here atomic number, which is proton number, is 6, while the neutron is 8. So as you can see, neutron varies from one atom to another atom. So for carbon 12, neutron is 6, carbon 13, neutron is 7, carbon 14, neutron is 8. And this is the reason why we have various or varying atomic masses, but the same atomic number, which we call isotope. It's a phenomenon. Now, after that, quickly, we're going to look at the second stuff we're discussing today, which we'll call isobar. Now, isobar is not so popular, but I can call it, it's more or less like the opposite of isotope. Now, when we talk about isobar is a phenomenon involving the atoms of various elements with the same atomic masses, but varying atomic numbers. Now, when we talk about isobar, it's simply the opposite, a complete contrast of isotope. Now, don't forget, for isotope, we are talking about the same element, Here we have 3 major atoms of carbon, just like we also have various atoms of hydrogen. Under hydrogen, we have protium, we have deuterium, and we have tritium. Hydrogen naturally has an atomic mass of 1, but for protium just have proton number of 1, neutron is 0. But for deuterium, proton is 1, neutron is 1, and then for tritium, proton is 1, then neutron is 2. So that's just for hydrogen also under isotope. Now, when we talk about isobar here, we're talking about a phenomenon whereby different atoms of various elements, not the same element, unlike isotope, have the same atomic mass but different atomic numbers. So we're going to be looking at this very example. Now look at carbon. This is not carbon 12, like what we discussed up there, like under the isotope. This is carbon 14. which has a proton number of 6, and then neutron number of 8. That is that for carbon 14. Naturally, carbon, the most popular kind of carbon is carbon 12, not carbon 14. So if you compare carbon 14 and nitrogen, this nitrogen 14, there's a natural nitrogen that that we're talking about here. So nitrogen here has an atomic mass unit of 14, and as you can see, the proton number, which is atomic number, is 7. So proton here is 7, neutron here is 7. Now, if we have to compare or juxtapose this, we have the same atomic mass unit, the same atomic masses for different elements, while we have various atomic number. So that's what we call isobar. It's a kind of phenomenon whereby we have the same atomic mass units, for various elements, while we have varying atomic number. So that is that for isobars. So, but today we are not really going to stay focused on isobars. We are going to stay focused on isotopes. So quickly, we're going to be looking at another thing under isotope. Now, under isotope, it's something we call isotopic abundance. Now, isotopic abundance is simply the proportion or the concentration of various isotopes of elements in nature. They are often a percentage. They aid us to easily get the average atomic mass unit of an element. Now, when we talk about isotopic abundance, now, as you can see, if you look at carbon, for example, right here we have carbon 12, carbon 13, and we have carbon 14. Now, there's a fact, there's a major truth. Now, all these various atoms of carbon, all those various samples of atoms of carbon, let me say that, they exist in varying degrees or varying percentage in nature. For example, carbon 12 is the most popular kind of carbon in nature. So we have more percentage of carbon 12 in nature compared to carbon 13 and carbon 14. So when we talk about isotopic abundance, you're talking about the proportion, of existence or the percentage of existence of each of these atoms of element in nature. For example, carbon 12 could be 50% in nature, while carbon 13 could be, let's say, 30% in nature, then carbon 14 could be 20% in nature. So when we talk about isotopic abundance, we're talking about the various degree of existence of these various isotopes in nature, as simple as that. That's what isotopic abundance simply means. Now, isotopic abundance helps us to easily get the average relative atomic mass unit. Now, when we say average, we are talking about the reason why we call it average because of the fact that at the end of the day, we compare various atomic mass units, for various isotopes. That's why we call it average. So now, what isotopic abundance helps us to get is to help us to get the relative atomic mass unit of an element to a very high degree. It helps us to get the relative atomic mass of an element, to a high degree of accuracy. That's what isotopic abundance helps us to get. So from here on, we're going to be looking at what we call the relative atomic mass unit of various elements using isotopic abundance. Here, there's a formula for us to see. Now, relative atomic mass unit of an element, not just relative atomic mass unit, but average relative atomic mass unit, is gotten when we use this formula. That's isotope abundance. Isotope abundance is simply the percentage of that very isotope in nature over 100 times the relative atomic mass, RAM, don't forget, in our previous lesson, the short form RAM, of isotope over 1. Now, what do? We get the summation of all this. So if we want to get the relative atomic mass unit of an element, or the average relative atomic mass unit of an element, what we have to get is to get what we call the partial atomic mass of each isotopes. Now, all this here bring about what we call the partial atomic mass of a given isotope. So this is what it is. By the time we are given various samples of a given atomic mass unit of a given element, that is, we call it isotope. That's what the phenomenon is called. Now, by the time we are given this and we are given the percentage of their existence in nature, all we just have to do is to use the isotope abundance of 100 of each of the isotope given times the RAM of that isotope, that is the relative atomic mass unit of the isotope given. So by the time we get each of this, we end up having a summation of all of them to get what we call the relative atomic mass of a given element. As simple as that. So I call it the partial atomic mass of each isotopes. That's what I call it. The partial atomic mass of each isotopes. So as simple as that. So in the next lessons, we're going to be solving You're going to be doing calculations on isotopes and isotopic abundance. So I would love you to go ahead to learn all this because they will come in handy when it's time for us to solve or for us to calculate on, isotopic abundance. So at this very point in time, we're drawing the curtain of today's lesson. If you found this lesson resourceful, please subscribe to this very channel, share this lesson with others. See you in the next lesson. Thanks.